Thank you very much, and thank you for a nice introduction and also invitation here. It's a pleasure to be here. So what I'm going to discuss today is a little bit here. So introduction of what my group does in Meilahti, and then what we are focusing today is ovarian cancer and treatment, and also how we use mathematical modeling on that. And then we go through the some of the basic steps in cancer treatment, and also where I feel, so I have made this presentation so that what I think might be useful for you or interesting for you. So for example, histopathological image analysis is something where machine learning and AI is extremely important. So I'm showing you an example of that, and I hope that create some discussion. And also that in radiology there's lots of images and data that can be analyzed and should be analyzed. And also that we lastly take a look a little bit about genomics, what we typically do there in my lab. So a little bit about my lab. So the lab's official name is Systems Biology of Drug Resistance in Cancer. And the drug resistance itself is the most challenging issue in cancer care or oncology. Typically many cancer patients respond well to the therapy, but then for reasons that are related to mostly tumor evolution are getting resistance to cancers. And we want to, in my group, understand the mechanisms why and how the cancer cells become or tumors become resistant, and how to overcome them. So what drugs should be given to the patients so that this resistance is getting over. So our overall objective is to improve clinical management of cancer patients. So we are, like them already mentioned, we are in applied science. So my background, like is engineering. So I get in technical physics and studied systems theory and signal processing, applied mathematics. So we do some method development, but all our method development is focused on application. So we don't make methods or are interested in making something extremely fast or computationally effective. What we are interested in is making the method such that it answers a biological or medical problem. And what we do is the so-called systems biology approach. That means that we use large-scale data. Multi-level means that we use molecular and different kinds of molecular levels, and also clinical data. And as I said, we develop methods, but our focus is in application. And what we are interested in is making methods and applying them, but what we have to do as well is infrastructure. I'm showing you examples, but otherwise we can't just analyze the data and get anything out from there. So we have to also do some infrastructure, and that is something we have been doing quite a bit also in the past. And I just mentioned here that all we do is open science, so all our methods are freely available, and I hope that the tietosuojavaltuutettu, who is in charge of making statements of how data should be delivered, is also taking off his folio hat so that we can actually give the data. So we actually had, like last week, an hour discussion of lawyer in Helsinki University. Are we able to deliver the data that we have to a group inside University of Helsinki? Which is not the way we want to do. So we would like to deliver the data, give the data, and be highly collaborative inside the university and in Aalto, and also in the Meilahti and with the clinicians. So very happy to discuss that as well in the end. So as I said, we are focusing on drug resistance. Of course, it's a very large field. There are drugs that are targeted, that focus only one protein, or there are drugs like chemotherapy that hits everything where it's dividing cell. Now at the moment we are focusing on this lateral path, so the cancer chemotherapy, and especially the compound called platinum. It has been used more than 40 years in solid cancers. I'm highlighting the solid cancers because there are basically two kinds of cancers. Liquid cancers like leukemia, lymphoma, and so on, that are in blood, and they are typically much easier to manage and much easier to especially research, because you can get any time you can get samples. Solid cancers are much more difficult because you need always surgery in order to get any sample from the patients, and also that when they metastasize to brains and bones, that's something typically kills the patient pretty quick. So the platinum compounds are actually quite usefully used quite widely. It's been estimated that 20% of all drugs that are used in cancer patients have some kind of platinum compound in there. The typical response rate to platinum is like 80 or 90, so the patients typically respond extremely well in the beginning, but then they develop very quick resistance, and then this is something we are very interested in. And of course, when you get refractory, so refractory means that it's resistant to basically everything, these people typically have very short life expectancy. So basically our goal is to make platinum great again. So here are our research goals. So what kind of, if we have a chemotherapy, is the patient we are seeing gonna respond to the benefit from the chemotherapy? This is very important questions also from the clinical side. Platinum is such that if the patient is not given nausea drug, the patient will throw up every 5 minutes, so that's like 12 times in an hour. So the patients who do not benefit from platinum should not take that. So the other one is that what resistance mechanisms are active in patient diagnosis or during the radiation follow-up. What are the molecular characteristics? These are mostly research questions, and then what targeted therapy should be effective to the reverse chemoresistance. So when I took a look at these, our key research questions, I was thinking that, well, in here it may not sound that you need any machine learning for this. So I just put there at the first. So this one is actually prediction, so this supervised learning, and then as like this, but here we also need heavily databases, whereas these are more data mining enterprises, so we typically use unsupervised learning methods in these ones. So in principle, what we want to do, or our hypothesis is that when we hit, or when the patient is hit heavily with the chemotherapy, it's like giving hit with this like big ball. It really doesn't care what cells it's affecting. It's hitting everything. And then if that is combined cleverly with the targeted therapy, the combined effect should be that the tumor itself is eradicated. So that's what is our hypothesis and where we are getting at. So the cancer that we are talking about is ovarian cancer. I want to also emphasize here that there are different kinds of cancers. Like, I don't know how, you know breast cancer. What would you think, what is the cure rate? So what percent of the breast cancer patient is cured by today's treatments?
What does cure mean?
Cure means, excellent question. Cure means that you cancer-free more than 10 years. So if there's a person with the breast cancer and given a breast medication, how many percent are cancer-free?
65%.
65%.
80?
80? Great. We are getting better. So 95 is, I think, the latest. And the same with prostate cancer. I'm not saying that they are irrelevant. I'm saying that they are so, the breast cancer is so prevalent that this 5% or so is still, I think, 5th or 3rd largest cause of death for females. But I'm saying that in many cancers, the cure rates, and we are doing actually pretty good. But there are also cancers that are not cured that well. And one is glioblastoma, the brain cancer. Typically, everybody is dead in 5 years. Then there is pancreatic cancer. Practically everybody is dead in 5 years. And then ovarian cancer, when more than half are dead in 5 years. So we are focusing on this ovarian cancer, which is one of these so-called bad cancers. And its hallmarks is that it's very heterogeneous. It typically has very good initial response to platinum, but the majority of patients get the relapse and then they die in 2 to 3 years after diagnosis. So here are a few examples of ovarian cancer. So this is early ovarian cancer. You can see that the cancer is here. So it's easily removable because it's looking like like a coherent set of tumor. So when surgery alone helps and basically cures many of these patients. This is what we are looking much more. So this is disseminated ovarian cancer. You can see disseminating all of this stuff here is cancer, and this is actually the abdomen. These are guts. So you can see that there's no surgeon in the world who is able to get all these cancers away. So these people do need also chemotherapy. So typically these patients are given both chemotherapy and surgery. I give us like a spoiler here. I'm showing you this because we make a mathematical model of this part of this treatment schedule. So if the patient is seen in the diagnosis that her cancer can be removed, it's removed, and then this given adjuvant therapy just for the precaution and hope that they are doing well. If initially the patient is not seen that they can be operated, they are given 3 rounds of chemotherapy first, and then they are operated, and then they are given the standard treatment as well. So these are where the surgeons are, and then here we have also, because we are focusing on these patients, these are doing pretty poorly, right? So we are focusing on those patients that are in here, and this is marking that we get PET or CT images from these patients. And for research purposes, this is fantastically good thing. So first, here we get samples, and we get both fresh samples, blood samples, and radiological images. Then the patient is given 3 times of chemotherapy, and then they are operated again. So we get sample before and after the chemotherapy. And also the patients typically have some issues in when they are progressing again. So we get also sample from the relapses. So this so-called longitudinal sampling is not available for many like prostate cancer, breast cancer, lung cancers. You don't open people's lungs many times in their lifetime, right? Whereas you can open the abdomen a few times if the patient is healthy enough. And so research-wise, this is an excellent track to do, and this is what we are doing in the lab very heavily.
Excuse me.
Yes.
How many treatments like this is done?
Sorry.
Nowadays?
What do you mean by treatment? So,
I mean that how many operations like this?
It depends. We are focusing there's like 500 altogether in Finland, the ovarian cancer patients. And in Turku they have typically 1 to 2 patients who go here. In Helsinki they have 4 or 5 per week, I mean. So what we wanted to do is a mathematical model that models both the tumor evolution of the ovarian cancer and this treatment arm here. And what we did is we mostly used radiological images, which are coming here. So this is patient diagnosis, that means here. And then the second part is in here. So what we are seeing is this one is the cancer region. This is heart and spleen and testicle gonads, so, but which are highly metabolic. That's why they are seeing as a black. But here this is cancer. So you can see that a diagnosis there's huge amount of cancer, and then after 3 rounds of chemotherapy there is nothing. So this out of first time, when we do mathematical modeling, what we want to do when we are focusing on chemoresistance, we would like to know what is the effect of platinum. Typically it's taken from the hat or from cell line experiments, which really doesn't tell that much about this actual patient resistance. So for the first time we were able here to see how effective really is. So if there is a mass of 10 to the 9 cancer cells, and we are given 3 rounds of chemotherapy to the patient, what is the fraction of those cells that is available? So what is, or the distribution of that? So this was the first time we were able to do that, and we utilized that in making the stochastic model on the development of resistance, and we found out that these are our training set here, and this is our independent validation cohort, and this is this black line here is the model. So we see that it's actually doing pretty well. So what we are able to do now is so-called virtual patients. So we can simulate easily cohort of ovarian cancer patients whose treatment in general, so distribution of their treatment is almost identical what we are seeing in real life. Now, this gives us an opportunity to test first of all, see how many cancer development methods there are. So we can see that there is in general, there are 5 active resistance mechanisms at diagnosis, which is pretty bad, which would mean that if this would be equally important, you would need to give at least 5 different drugs to patient in order to get any benefit or get eradication of the tumor. But we see that in the beginning there's 80% of sensitive cells, and at the chemotherapy, after chemotherapy, there's 80% that have at least one resistant mechanism active. So it means that they are not equally distributed, but there are few resistant mechanisms that are dominant. And this gives a rise for us that what we are looking at here from the actual molecular data from our patients, that how many drugs we need to use in addition to chemotherapy in order to get clinical benefit. So here is the standard treatment, and if you apply one effective drug that attacks the one resistant mechanisms, you get huge benefit. If you add another one, you get also huge benefit, but not that much anymore. And the third one, you get a bit more, less, and after fourth, you basically see no benefit. And the reason is that these subclones of these resistant mechanisms are so small that even if you have highly beneficial drug, it really doesn't matter anymore. So the important thing is that is coming out from this was published half a year ago in cancer research, is that if there is that if we are able to find the most dominant or two most dominant mechanisms from the patient, we will get actually, and there is an available effective treatment for those, we will get a very large benefit. And this was just our first step to the radiology. There is a huge amount of CT scans, PET scans, and so on. And you can just imagine that there is in Meilahti there are several radiologists who are just would love to have the pile of zip here and analyzed. So this is also something that you may want if you are interested in applying machine learning AI methods. Radiology is something that you may want to consider. The second one that I would like to show here is the pathological image analysis. I'm very happy to have Valeria here, who has actually done all this. So if I say something stupid, just correct me. And also if you have any questions, so Valeria is able to answer. So when all the patients who get to the clinic and are diagnosed with cancer, before they are diagnosed, they are given a sample from the prospective tumor, and that is stained with hematoxin and eosin, so-called HE staining. So now I rephrase: every cancer patient is stained with these ones. So you can imagine that there are huge amounts of slides looking like this, where you have full clinical history, and you can also have these pathological images. What you can see from here is actually quite a bit. So you can see cancer cells, cancer cells, immune cells, stromal cells, and vesicles. And this area is so-called digital pathology, so making digital slides of these and then analyzing those, typically with deep learning methods now. If there's nothing that hasn't been analyzed with deep learning. But anyway, so there's been actually quite nice results from analysis of deep learning neural networks on this one. So I think Johan Lundin is very, very good in this one. So this is also one thing that you may want to consider. So our step in here is...
Did you try pigeons?
Sorry?
Pigeons, the birds. You haven't heard about that study?
No.
So they got the good results in classifying such images with a bunch of pigeons as well, just using them in an identical fashion as deep learning.
They would eat the samples.
No. They would get even seeds as a report. So their vision system is similar, apparently.
That's cool. We should have it that's fantastic. I'm looking forward to that. I want to move here as well. You know, you have fun here actually. So anyway, so what we are doing is that we are obtaining these samples from clinic. So I don't know if you see it, this minimum of 18 image, maximum of 1,163 images, and mean of 504 images per patient. And how big is one image?
I think in the order of
gigabytes. So this is actually for one patient. So you know you get actually quite a bit of stuff, and this is some, and then to have 500 images. So first of all, analyze those properly, and then store the data and combine them is actually something to do. So we have this computational method to do that. So this is more like a traditional machine learning, right? So we don't just put them to deep learning or birdies. We actually do color adjustment, then we do real segmentation, and you can see it from here. So this tells that we correlated our machine learning system that identifies the spots in here with the pathologist, and our concordance like 96% about, so we are pretty happy about that. So all these circles are automatically identified. You can see that there's some mistakes here and there, but the basic thing is that we are able to automatically find the cancer cells, lymphocytes, stromal cells, and endovasculatory cells. And then from those we can use actually quite a bit of difference of the size, the roundness, and so on, and calculate these kind of morphological features and also textural features, which I think very important is that this kind of taking a look at the areas. So do we have lots of like a cluster of cancer cells? Do we have immune cells here and so on? So in here, what we wanted to do is to predict whether the patient responds to chemotherapy, which is not actually done before. So when patient is given chemotherapy, the medical doctors really don't know whether she is going to respond or not. And you know, there's lots of RNA and DNA and other studies that try to predict that, but there's nothing there. So we just take a look at, how much information we gain if we just take a look at this HE stain that has been developed in like 1850 or so. How much information we gain from here, and it's actually pretty good. I was surprised to see that, okay, we have only 52 patients, but with random forest and leaf one outcross validation, we got the area under curve 82, which is surprisingly good for me. I was expecting much lower. And now we have also much other data for this, so we can also combine other clinical data and molecular data. But this is actually a very nice result, and we should be writing with Valeria all the time this manuscript about this. This is an unpublished result. So the point in here is that there is in digital pathology, there is quite a bit of opportunities to use any machine learning way, like this deep learning way or the standard way where you have segmentation or feature extraction and then training. So now I'll go a little bit more to the molecular side. I'm not going to discuss this lengthy. So we have a EU project that's called Hercules. You can see that comes from the comprehensive characterization and effective, and so you can perhaps see which was first the name or the acronym. But what we are doing here is that we identify characterize chemoresistant high-grade serous, so ovarian cancer cells, basically using the idea that I showed you earlier. So we have patients before and after chemotherapy. We do single cell proteomics, single cell RNA-seq, standard sequencing, and then we hope to find here the characteristics of the cells, then identify them in other patients, and then use a Christer Wennerberg drug screening method to identify the combinations that most likely affect or kill those cells. And this is our consortium, so we are actually quite big, and we are, like in all EU applications, we are pretty, yes, thanks. So I'm just saying now this is prospectively collected patients. It means that they are still alive, or most of them are. So we don't even know whether if they operated like 2 months ago, whether they're going to respond well or not. But so therefore we expect to see the kind of convincing results later on. This is the celebration is for 100 recruited patients. So now we have 270 whole genome, 208 RNA-seq, single cell, and proteomics, and we have altogether 1.5 petabyte of data just from these patients alone. And this is now something we are very heavily doing. Also, if you are interested in this, I'm very happy to continue discussion with you. And as I said briefly about infrastructure, so we have so much data and so many data levels like methylation, RNA-seq, whole genome, single cell, single proteomics, liquid biopsies, and clinical data that we actually need an infrastructure. So we have our own Unreal-based computational ecosystem that has been published 8 years ago, and now we are publishing we converted to Scala, so we are now having another paper on that very shortly. And then we actually, we have developed a clinical database to manage the clinical data and combine that to the data, and also that then taking out the data and having securely there in our custody. So I just note here a few things. I try to be fast. So most of the time what we do is going to getting the data to the analyzable form. I just lectured clinical data mining here in LSI. Not here, but in Meilahti. Who was there? Anyone? Okay, so one of the feedback of the courses was prevalent, and I really didn't want to spend that much time of making this Excel file or this clinical data useful for R. And there, we had high fives and toes that this was exactly what we want them to understand. That 80% of the time in our project actually goes there to make the data available, that you can apply that fancy algorithm there. So that's something we spend a lot of time. Systematic biases, I think Antti Häkkinen was here to discuss those last year. So there's a systematic bias on tumor fraction of before and after chemotherapy, so we have to correct that, and that's been doing. And even if you are using openly accessed data that should be highly correlated, like the Cancer Genome Atlas, there's quite a bit of things to do. For example, my summer student found out 13 different ways to misspell paclitaxel in there in more than 1,000 patients. He was unhappy about that and consequently changed lab. So, or never about that, of course. And like the HE images, when you take a look at those, 25% of them have like huge errors, like you see a fingerprint of the technician who has done the sprint, or you see something like this there. And if you don't take those into account and just take the data and analyze that, that's going to be a disaster. Well, perhaps you can still say something, but for sure that's not going to be very convincing. So what I'm saying is the plug and play opportunities without so-called middle layer are rare. I'm going to get later on what this middle layer are in the discussion. The last 2 minutes I want to stay in something I'm very, very excited about, and this is circulated tumor DNA. So the tumors leak their DNA in the blood, and you can sample that from the blood and then use ultra high sequence, deep high sequencing to take the mutations there. So we have analyzed this, and we developed a computational pipeline and on database to link the mutations we found in the blood to the drugs that might be useful for those ones. And here we try to optimize the treatment of ovarian cancer patients using more than 500 genes. So we have 12 patients, and I'm not going to go this through. This is an example. So basically, what we have, we analyzed this, we found clinically applicable or develop active mutations or copy number results in more than half of them. Some of the patients died before we were able to change their therapy based on these results. But there was one patient who we found out that there's ERP2 amplification is showing here, and then we validated that in the HE or the histopathological slides. And then her treatment was changed to paclitaxel platinum to include something else. So I'm not showing this one here. So this is the patient in the diagnosis. You can see the tumor burden measured by this biomarker is really high. When there is the surgery, so then there is given the platinum and taxane, the standard treatment, so the NAC patient, so giving 3 cycles of these before the surgeon. So the tumor volume goes down, and then there's a surgery, it stays down, and they're given maintenance treatment here, and then another drug, and she was also part of the trial. But then you can see that it's after 6 or so months, it's getting up again. and then they changed to the next line treatment, so doxorubicin. It has no effect whatsoever. No, I hope she is also from placebo and not from olariparib, because it means that, that also this part of clinical trial had no effect. So she is getting cancer. So and here we suggested that she could also have that this trastuzumab is HER2 or ERB2 antagonizing targeted treatment. So we suggested that if that is added to her treatment schedule, that should take care of the resistant mechanism that she has developed to this platinum and paclitaxel. So they were changing her treatment here, and you can see immediate and fast drop of the tumor burden. And that was last spring, and I think she's still doing pretty good. I'm not, I need to discuss, we have new samples from her, so we don't really know if she's getting back. Eventually, she is getting back to tumor. It's just a matter of time. But now we have also samples from here, so we can perhaps suggest what would be the next treatment. But we are very happy to see that our prediction was proved true in real patient, and also that now we have these longitudinal samples from this. So in summary, cancer research and oncology, so the difference is that oncology is focusing on treatment of patients. They come data research, lots of data there. And they really need, and they want to use everything you do here in Naalda. And in decision making and in methods. And I want to say that the clinical data, the data requires quite a bit of work, and there are several. So this is the middle layer. So there are many groups in Meilahti who are willing and eager to help you in this. I don't know how much you want to spend time cleaning the clinical data or getting out these poor quality images. So we have done that. So we have the so-called many data sets that are curated already and could be perhaps easier to be used in testing different methods and so on. So my group is that. Then there is Johan Lundin. Then there is Ying Tang. There is Samuli Ripatti, Lauri Aaltonen, and so on. Jussi Taipale. So there's many groups who are very eager to collaborate. And my group focuses on applying machine learning methods, and as I said, we want to tackle real-world cost issues. And this is our lab like a few years ago, and I'm very happy with the collaboration with pathologists, oncologists, and also that Anina Pärkkilä, who is soon coming back from Harvard to here to our research program to collaborate more. So sorry about being a bit over time, and very happy to now continue the discussion.
Well, thanks